Hello and welcome everyone. So this is the second lecture on Riemannian geometry. The last video was an aside video on a crucial topic of tangent spaces on prerequisite. This is actually the second video on Riemannian geometry, and today I'm going to discuss an example of Riemannian manifold. But before I do, let's recall what was the Riemannian metric and let me make important point. Okay, so recall. How did we define the Riemannian metric? You have your smooth manifold and some point P belongs to M. And at each point of the smooth manifold, you have the corresponding tangent space, TPM. And in that corresponding tangent space, you define an inner product. Okay, so that inner product was TPM cross TPM to R. Now, first point to note that you are defining this inner product at each point. At each point, you have the tangent space, and there you are providing the inner product. So you see, Riemannian metric is not just this one inner product. It is an entire family of inner product, and that is why when we define the Riemannian metric in terms of tensor, what do we say? That it's a tensor field, because at each point you are providing an inner product. Okay, so this is the first point to keep in mind, that Riemannian metric is a family of inner products. Okay, and we found the local expression for that. That local expression was g of x comma y is equals to summation I comma j gij xi yj, and these gij were the components of the Riemannian metric. Xi and yj are the ith and jth component of the vector x and y. Now, this is also written as, also, this is another point to note, also, this is also written as the line element, which is ds squared summation I comma j gij dxi dxj. So this thing is called line element. This gives you the Riemannian metric. Now, let me first explain these things here, dxi and dxj. These xi and xj are actually the component function. You are in the manifold at the point P belongs to M. So corresponding to this point, you have the chart u comma x. This x is the map from u to Rn, or to some open subset, not exactly Rn. Write, I should actually write x of u contained in Rn. Okay. So this is your chart map or coordinate map. Corresponding to this coordinate map, you have the component functions xi, which goes from u to r. So these are the component functions that we have here. But what exactly dxi and dxj are? To explain that, recall from the manifold theory, you had something called differential. So differential map in general you can define for the smooth function from one manifold to another manifold. But right now I'm concerned with these type of function which goes from U to R. So I will define it for function. Let's say you have the function f from the smooth manifold M of dimension n. This n is not the power, it just represents the dimension of the given manifold. So I will take this function f, from the manifold to R. Then the differential of f at the point P is, see, these are the things from the manifold theory in the prerequisite, but I am recalling it just to give you an idea of what these dxi and dxj are. So I will not go into the detail of the differential. I will quickly do the calculation. So this differential is basically the map which is denoted by df. This goes from the tangent space at the point P on the manifold M to the tangent space at the point f of P on R, which is nothing but is actually R. Okay. This is given by df of v comes from TPM, the vector. And how does it work? How do we define? The tangent vector at the point P, this operates on the function f. Okay. Now locally, this is just a map, but locally, what is it? Well, locally, you see, you can write this vector v, which is coming from the TPM. You can write vector v in terms of the chart-induced basis. So you can write it summation vj del over del xj, where sum runs over j. Now, df is just a linear map. So this will satisfy the properties. You can take the summation out. You can take the component vj's out, right? And then this df will operate on these del over del xj. So what this will become? This will become summation j vj del f over del xj. Well, that's the definition of the df. V operates on the function, so here v is del over del xj, so this will operate on the function f. Now this was for the function f. For the component function, now let's see for the component function. The component function is xi. So what is the differential of this xi? Let's first calculate for the component function for the basis vectors. That is del over del xj. What this will be? Well, this will be nothing but del xi over del xj. And you know exactly what this is. This is nothing but your delta ij, the Kronecker delta, which has the value 1 for I equals to j and 0 for I not equals to j, right? Now, again, let's find it out. dxi, if you have any vector v, then that any vector v can be written as okay, you can write it in this manner. Again, doing the same thing, you get vj and then dxi This will operate on del over del xj. Now here, this thing is equals to delta ij. But you see one thing, the sum runs over j the moment for all the values of j which are not equals to I. When j is not equals to I, this is going to be 0. That doesn't matter. The only value that matters is j equals to I. So this is equals to vi. So you see what's happening? When you find the differential of the coordinate map and you operate on any vector, this gives you the ith component of that vector. So that is for each I, the linear function dxi reads off the ith component of any vector v. Okay, and so that is why, so now you understand this thing, summation I comma j gij dxi dxj. Gij are simply the component of the Riemannian matrix, and dxi dxj provides you ith and jth component of the vectors. And one more thing, this juxtaposition of differentials here, this thing, differential here, this simply represents the ordinary multiplication of functions on each tangent space. But where does this notation of ds square and line element actually comes from? One way to understand that thing is, let's say you have 2 points P and P dash. These are your nearby points. Okay, and you have the coordinate for the point P x1 to xn. Okay, and for P dash, which is the nearby point to P, the coordinates are x1 plus delta x1 up to and so on xn plus delta xn. These are the coordinates. Then the tangent let's say delta p summation delta xi del over del xi. You see what you are doing here, you are taking these basis vectors, scaling them by del xi, which is actually the difference between the coordinates of these two nearby points. So approximately this tangent vector at the point P points to P dash. This will point towards the P dash. So the distance between the point P and P dash, so the square of the distance delta S from P to P dash is approximately equal to delta P square. This is nothing but the inner product of delta P comma delta P. That's how you define the norm in inner product spaces. Now if you put the value of delta P and you apply the properties, that you can take summation out, you can take these delta xi and delta xj's out, and you will get summation, this inner product of del over del xi and del over del xj. These are represented by gij. We have already done this kind of calculation, so I'm not doing it again. Okay, delta xi and delta xj, and this is from where we get this different notation, the line element kind of notation. ds squared equals to summation ij gij dxi dxj, and for all the calculation purposes this is the best expression that we have, and it is easy to do all the calculation. So now I hope you understand this different expression for the Riemannian metric in terms of line element. Now let's use that to find the Riemannian metric. So let's consider an example. The first example is Rn, the Euclidean space. Now I will find the Riemannian metric in two coordinates. First Cartesian coordinates and other one is polar coordinates. So let's first consider the Cartesian coordinates. And I will do it in R2. Okay. So if you have done the proof of the fact that R2 is a topological manifold, you know what the chart map is. The corresponding chart map, let's say phi, what is this? Well, you take your open set on R2 and you go in some open set of Rn, right? What's the chart map that you are going to define here? Well, this is simply the identity map. You can simply define identity map. Okay. Well, in that case, the basis vectors that we need are simply del phi over del x, which is your 1, 0, and del phi over del y, which is your 0, 1. Then what is the gij? Then gij is nothing but g of del phi over del xi and del phi over del xj. So let me write it in this manner also. This is your x1 and this is your x2. x1 is x, x2 is y. Okay. So now let's find out G11. So G11 will be del phi over del x, comma del phi over del x. So this is the dot product of 1, 0 with 1, 0 itself, which is del phi over del x. Del phi over del x is 1, 0. So this is equals to 1. What is G22? Well, in the similar manner, this is g of del phi over del y, del phi over del y. Del phi over del y is 0, 1. So this is the dot product of these two, and this is again 1. Okay. What else do we need? Well, we need G12. What is G12? G12 is G of del phi over del x, comma del phi over del y. So this is the dot product of 1, 0 with 0, 1. Well, this will simply be 0. Now what will be G21? Well, metric is symmetric. So G21 is nothing but equals to G12 and hence 0. So we have got this our component matrix Gij. You can write it in terms of matrix. And this is your identity matrix. Now let's find the line element. Okay. So you had dxi, dxa and your matrix. So you write it, the line element you get in terms of matrix, you write dx, dy. This is your Gij's and dx, dy. You calculate it, when you multiply these two, you will get dx, dy what this will be equals to? Well, this will be equals to dx square plus dy square. And if you remember, this exactly used to be the line element in our Euclidean geometry, right? This is exactly the line element, and this used to come from the usual inner product, which is the dot product, and that's what we have here. Okay. How do you use to find the line element? Well, if you have the curve, so I hope, let me not discuss that. I hope you know that because that used to come from the Pythagoras theorem. You used to take. Okay, let me do that. Let me do that. So you have your curve, and you used to take these infinitesimals, right? You draw the perpendiculars, and you apply the Pythagorean theorem. Okay, so that you know already. So now this is the line element in the Cartesian coordinates. Now let's go to the polar coordinates, and in polar coordinates we will do the similar thing. So in polar coordinates, what we wish to do? Well, we have the Cartesian coordinate xy, and from there we're going to go into r comma theta. Now we already know our parameterization, which is x equals to r cos theta and y equals to r sin theta, right? What we need now is we need the basis vectors del over del r and del over del theta using the information that we have here. How do we find that out? You have x and y, you have your del over del x and del over del y. Well, you can use that. You can apply the chain rule and you can find this del over del r and del over del theta. How do you do that? Well, this is del x over del r into del over del x plus del y over del r into del over del y. And this del over del theta, this is in the similar manner del x over del theta, del over del x plus del y over del theta, del over del y. So this is from chain rule. Okay, now we have the basis vector and we know what is the explicit expression for x and y. So let's use that and find exactly what these are. These will be, what is del over del r? Well, del x over del r is simply cos theta. So this is cos theta del over del x plus del y over del r is sin theta. So this is sin theta del over del y. In similar manner, del over del theta is minus r sin theta del over del x plus r cos theta del over del y. Well, I think our work is done because we have the basis vector, then we can find the component matrix, the metric component matrix. So what are the components? The first one is GRR. What is GRR? Well, GRR is simply G of del over del R and del over del R. This is the dot product of this. So use this expression that we have here to find the dot product. What's the dot product? Dot product is simply cos square theta plus sin square theta, which is equals to 1. Similarly, g theta theta is del over del theta dot product del over del theta. That will be, you can take r out, so this will be r squared sin square theta plus cos square theta. So this is equals to r square. What is gr theta? Well, in case of gr theta, you take the dot product of del over del r and del over del theta. I hope you all know how to do the dot product. So clearly you can see that you can take r as common and then you will have cos theta and this minus sin theta. So minus cos theta sin theta plus you will have plus sin theta cos theta. These two will cancel out and you will get the 0. And again, g theta r is nothing but equals to gr theta. So this is also 0. So in case of polar coordinate, the matrix of the Riemannian components of the components of the Riemannian matrix for that is 1 0 0 r square. The diagonal elements are g r r and g theta theta, and those are 1 and r square, and off diagonal elements are 0. So now, how do you find the line element? The line element is dr d theta, the component matrix 1 0 0 r square, and this dr d theta. And if you multiply it, you will get dr r square d theta multiply with this vector dr d theta. This gives you ds squared equals to dr square plus r square d theta square, and this used to be the line element in polar coordinates in Euclidean geometry. So you see, this is how we find out the line element of the metric on a Riemannian manifold. So this was just the first example, which is the very basic example, but I wanted to explain it in details. Now the second example would be your sphere, but that I will not discuss in this video because I want you to first, so in case of sphere, let's say S2, please check that S2 is a topological manifold. Please check it. There are various ways to do it. Why do I want you to check it? Because you see, to derive the Riemannian metric, we first need the chart map. But what will be the chart map here? You can't simply say that the chart maps are always homeomorphism. Now you can't simply say that this is homeomorphic to some open subset of R2. Because you see, S2 and R2 are not homeomorphic. S2 and R2 are not homeomorphic. Because if they were, then you know that S2 is compact. If S2 and R2 are homeomorphic, then R2 must be compact. But R2 is not compact. So usually the expression for the chart map, the explicit expression is usually written in the book, but sometimes we don't pay attention. So please pay attention how they are defining the chart map, what exactly is going on. So please pay attention, revise it very carefully, and then in the next video I will do this example of sphere in great detail, just as I did here for the Euclidean space. I hope you understand all the calculation now, how to calculate the Riemannian metric. Thank you for watching the video.